Hello, in this video we will wrap up our discussion of one-dimensional quantum mechanics by talking about the 5 postulates of quantum mechanics. Now, I call these postulates because all of quantum theory can follow from them. They're fundamental in the sense that they can't be derived from other things. Rather, their justification comes from the fact that they are consistent with experiments. When you take 421, we'll begin sort of by thinking about the postulates. Here you should think of this as really a summing up of everything we've learned about quantum mechanics so far. Okay, so the first two are probably not too much of a surprise. So the idea that first, particles are described by wave functions. We've been talking about this for a while. And maybe one thing I'll emphasize here is that the wave function psi of xt, I'll allow for full time dependence here, contains all possible information about my particle. Oops, all second, as we talked about last time, observables are associated with operators. So the most important operators we talked about, right, are position and momentum, and then energy, which we call the Hamiltonian operator, H. Okay, so far not too much of a surprise. The next postulate is probably the most complex one, having to do with measurement. So as we've learned, measurements of an observable of the operator associated with an observable can only yield one of the eigenvalues of that operator. The best example of this is energy. So remember when we first looked at the infinite square well. You know that the infinite square well has discrete energy eigenvalues. And we've talked about, right, if you measure the energy of a particle in an infinite square well, you will only ever get one of those energy eigenvalues. If the particle is not in an energy eigenstate, right, there'll be different probabilities for getting different eigenvalues, but you will always get one of the eigenvalues. Then that sort of brings us to the next part of this, which is probability. So the probability of obtaining the result, which I'll call little a, has to do with is a probability given by the inner product we talked about a couple of classes ago. So as we talked about, so again, energy is the best example. You can always expand an arbitrary wave function as a sum of energy eigenstates where you have these expansion coefficients. And the idea is that we find those coefficients, and I should say this should be modulus squared here. And we find those coefficients by taking the inner product, so multiply your arbitrary wave function by the complex conjugate of the eigenstate and integrate over all of space. So again, some sort of not really any new content here. The next postulate we should think about is time evolution. So as we talked about when we introduced it, right, time evolution for wave functions is governed by the time dependent Schrödinger equation, which looks like this. So remember, we went through the separation of variables argument, and we found out that if we have energy eigenstates, those time evolve in a particularly nice way, right? An energy eigenstate time evolves with a factor of e to the minus I e T over H bar. And we've seen how if I have some arbitrary state, I can predict that state's time evolution by expressing that arbitrary state as a sum of energy eigenstates and then time evolving each of the eigenstates. And all of that follows, albeit with a somewhat lengthy argument, from the time-dependent Schrödinger equation. Okay. So the last postulate of quantum mechanics is probably the strangest one. It's the idea of collapse. Namely that if I have a wave function and I measure some observable corresponding to operator capital A hat, and I get the eigenvalue little a, well, immediately after measurement, the wave function collapses to the associated eigenfunction psi a of x. So again, we've seen this in a couple of places, right? So think about energy, right? So you saw in the reading. So if I had some wave function, so let's just say that this psi. I'll write this as psi of x, right? If we had this something like c1 psi 1 of x plus c2 psi 2 of x, right, where psi 1 and psi 2 are energy eigenstates, and psi is arbitrary, right? If I go and measure the energy of this particle, and I get the energy E1 associated with this eigenfunction, right, the wave function immediately changes after my measurement to that energy eigenfunction. So this is probably the strangest postulate of quantum mechanics. If you're bothered by it, you're in really good company, and I would even go so far to say you should be a little bit bothered that somehow measurement affects system, and that there's no way to measure a system in general without affecting it in some way and changing its state. So this leads to all sorts of interesting things to think about, and I'll just mention one really briefly. So imagine I had a particle that was in some wonky state that was not localized. So let's say I had a psi of x that looks something like this. So let's say I had something that looks like a blob. So if I go and measure position, and I detect the particle somewhere, so let me draw a new set of axes, what that means is that I'm going to have changed my wave function from this delocalized thing. So let's say I found my particle right here. I'm going to change the wave function to the position eigenstate associated with that position. And we haven't talked a whole lot about what position eigenstates look like, but it's a state with definite position. And if you think about it, it might not be too hard to convince yourself that what this is a function that's a very narrow, sort of very sharp spike right there. So you're going to end up changing the wave function to something that looks like this. Okay, so those are the 5 postulates of quantum mechanics. Here they are typed up on a slide for handy reference. Again, think of this as a nice summary of everything we've learned so far, and if you take 421, we'll revisit these and sort of come at them afresh from the perspective of thinking about spin, which is something to do with hydrogen that we'll sort of get up to the point of in the next couple of classes, up to we'll end where 421 is going to begin. So in the rest of the time before I get back today, what you'll be doing with Antara is you'll be going over some stuff about the qualitative nature of the hydrogen atom energy eigenstates that you read about. We'll get back and then we'll start to talk about the nitty-gritty of doing quantum mechanics in more than one dimension. Thank you very much, and I'll see you in a little bit.